Hi, this lesson is on rotational equilibrium, and you should watch this lesson and take notes on it after you've watched the video on torque. So we're going to just make a statement here about this term equilibrium. And in physics, the idea of equilibrium is really the idea of balance. Equilibrium is an idea that we met first semester when we talked about the forces canceling out on an object. So we talked about translational equilibrium. And so we said that when the net force is equal to 0 on an object, there will be no acceleration. I'll just write accel. Okay, now a picture is worth 1,000 words. So how about we just draw an object, a mass. And so if you have a force F1 that pushes the mass to the right, that mass is going to accelerate. However, if you apply a second force in the opposite direction, and you make it the same size, now you have an F net equal to 0, and the acceleration of that mass will be 0. So that's a very important idea from first semester, and we would say that the mass is in equilibrium. Okay, and when you say something doesn't accelerate, that just means its velocity doesn't change. In many cases, the velocity is 0, so the object remains at rest. Or sometimes the velocity might not be 0, but if it's not, it won't be accelerating under these circumstances. Okay. Now, the new thing here is let's talk about rotational equilibrium. And the condition for rotational equilibrium is when the net torque is equal to 0, you're going to have no acceleration. But it's a different type of acceleration. It's a rotational acceleration. And that means that the object won't just suddenly start spinning in one direction or another. Okay? So, for example, we talked about having a meter stick with a pivot in the middle, and we can see pretty easily that when you apply a force at this end and an equal force over at this end, where these distances are equal to the pivot, that in that case your net torque is equal to 0. So, right, because this force over here is going to tend to cause a torque in that direction. That's like a torque 1, clockwise. But that torque 1 is going to be canceled out by the other one. And so these two things cancel, and that means that you're not going to have any rotation. Okay? So the meter stick remains balanced. So that's important, that the torques have to cancel to achieve balance. If the torques do not cancel, if you have a situation like this, where we make one of those forces bigger and one smaller, well, now your net torque is not 0, and you're going to have a rotational acceleration. Okay. We haven't really defined it yet, but there is actually a symbol for rotational acceleration. That symbol is an alpha. We'll learn about that later. But for now, we're just going to say that if something, that alpha is going to be 0 when the net torque is 0. And that just means that an object doesn't suddenly start to rotate. Okay? Let's just do quick examples on your homework so that you can be comfortable with how to do these. So if you want to find your homework, we could take a look at the first example This is the net torque in equilibrium practice. And what you can do in these examples is what you have to do is to figure out what is the net torque on these objects. Now, they might be in equilibrium or they might not be. We have to find out. So the first thing you want to do when you look at these pictures is to look at where the pivot is. That's really important. So in this case, the pivot is going to be at the 30 centimeter mark on the ruler. Now, the next thing I want to do is go and look at all the forces, and I want to kind of visualize which way they tend to rotate this meter stick. This 10 newtons is going to tend to cause a rotation that way, around that pivot. And you have to imagine that. That would be a clockwise rotation. This 10 newtons down here is acting in the other direction. If that's your pivot, this 10 newtons works that way, and that's counterclockwise. Over here, this 10 newtons is going to also go counterclockwise. And again, you have to imagine what would happen if you just held this meter stick fixed at the pivot. And this force over here would be a clockwise, this would be a clockwise torque at the end. So what you want to do here is find the total clockwise torques, and then you want to find the total counterclockwise torques. And if they cancel, the object is in an equilibrium. And if they don't cancel, it's not. So let's do the clockwise torques first. We have a force of 10 newtons times a distance, an R, of 30 centimeters, 0.3 meters. We also have a contribution from this force out here. That would be plus 10 newtons times, let's see, from 30 to 80, it's 0.6 meters. Okay, 90 minus 30, 0.6. And so these are the two things that contribute. So what you end up with is 3 plus 6, or 9 Newton meters clockwise. For the counterclockwise, you would have 10 newtons times 0.1 meters, right, because it's 10 centimeters. You would also have 10 newtons here times 0.3 meters. So 10 times 1 is 1, 10 times 0.3 is 3. That gives you a total of 4 Newton meters counterclockwise. Okay, so what we've done is added up 4 different torques. 2 of them are clockwise, 2 of them are counterclockwise. We have to use the diagram to figure out which directions they go in. Then you get the totals, you compare them, and there is a difference of 5, and the winner is clockwise. 5 Newton meters clockwise. And that is your net torque. So that's how you do these problems, is to see if they're in equilibrium or not. So this is not an equilibrium in this particular example. In fact, I don't think any of these the next three are. But it's just the idea of practicing to get net torque. Okay. On the flip side of this assignment, you're going to do something very similar to the activity in class today. You are going to find the missing mass. Okay. And you're going to do that by balancing the torques. Okay, and so we're going to say that the torques that go clockwise, actually, why don't we say torques that are counterclockwise must be equal to torques that are clockwise. This one is counterclockwise. These two are both clockwise. So mathematically, you can set this up by saying 250 times, times 50 minus 20, 30 centimeters. Oh, yeah, I'm using grams here and centimeters. Is that okay? Sure. Because if I were to convert this into newtons and this into meters, those conversions would just all cancel out. So shortcut, just use grams times centimeters. On the other side, you'll have 150 grams times 10 centimeters plus m times 40 centimeters. So again, you have to identify which directions those go in. So now you do some math, and we've got 250 times 30 would be 7,500. This becomes 1,500 plus 40m. We subtract off. That becomes 6,000 equals 40m. And m is going to be 6,000 divided by 40, which would be 150. And those units should be in grams because it should be. Okay. So that's the mass it would take to cancel out and put this in equilibrium. By the way, the meter stick itself is being supported by this nice pivot, which is right here, which has to apply an upwards force. This is the force of the pivot. And that force of the pivot should be equal to the total of all those downwards forces. So it would be the total of 250 grams plus 150 grams plus, again, 150 grams. So 300, this would be 550 grams. You might say correctly that that's not a force, Dr. Schultz, that's a mass. You're right. If you want to convert it to newtons, you would do 0.55 kilograms times about, 9.8 or 10. So that's going to be about 5.5 newtons, approximately. Okay. And so that's actually the force that the pivot provides. And notice that that force cancels all the downwards forces, so that this meter stick is in equilibrium in a translational sense too. So give that a try and see if you can work out the next three to find the missing mass. Good luck.